Some nights feel different, not louder, not quieter, just different. You look up and the sky looks back, holding questions older than anyone alive. Stars you'll never reach. Light that left home before you were born. September 2024. A telescope in Hawaii catches something moving wrong, too fast, too bright. Trajectory that doesn't fit the math we've built over centuries. They name it 3I Atlas, the third visitor from beyond our solar system we've ever confirmed. The first two were strange enough. This one breaks different rules. You're hearing about it now because it's doing something tonight that shouldn't be possible according to every model of celestial mechanics we trust. Before we drift into that mystery together, a soft invitation. If these quiet journeys feel like home to you, you might want to stay connected. You can gently tap the like button when it feels right. Subscribe if you'd like more nights like this one. Ring the bell not for noise, but so the next story can find you when you need it. No pressure, just an open door. Now let's breathe and wander. Tonight we're following something that doesn't belong. An object traveling at 140,000 miles per hour, carrying chemistry. Our solar system doesn't make glowing brighter than it should, following a path gravity alone can't explain. 3I's Atlas passed closest to our sun on October 13th, 2024. What telescopes saw raised more questions than answers. You don't need a degree in astrophysics, just curiosity about something beautiful and impossible happening in the dark above us. Sometimes the universe whispers, sometimes it shouts. Sometimes it just does something that makes every scientist stop and say, wait. Numbers tell stories when you listen closely. 3I's Atlas has an eccentricity of 1.02. Anything above 1.0 means the object isn't bound to our sun, not orbiting, just passing through. That 0. 02 above 1 is the difference between a visitor and a prisoner, between a story with an ending and a loop that never closes. Its velocity doesn't point back to any known star system within 300 light years. Computer models trace backwards through millions of years. Every simulation ended at the same place nowhere we can identify. It's not from any neighborhood we recognize, not heading anywhere we can predict. Just here now, moving through our corner of space like a message in a language we're still learning to read. Maybe you've driven through a town at 3 a.m. once, empty streets, lights on timers. That feeling of passing through something that exists whether you're there or not. 3I Atlas is doing that to our solar system, passing through while we watch, barely slowing, already gone by the time we finish looking. The Panoramic Survey Telescope. Pan-STARRS caught it first. September 13th, 2024. A dot moving differently than the 10,000 other dots tracked that night. Within 48 hours, orbital calculations confirmed what the numbers suggested. This came from beyond. Oumuamua passed through in 2017, cigar-shaped, accelerated strangely, no tail. Questions it left behind still don't have clean answers. 2I Borisov arrived in 2019. Proper comet, had a tail. Chemistry matched our solar system's comets. Interstellar, but familiar. 3I Atlas is different. Chemistry stranger than Borisov. Brightness behavior unexplained like Oumuamua. Something in between or something entirely new. Dr. Elena Kashuba's team at the European Southern Observatory found absorption features in October 2024, carbon dioxide and methane ices in ratios that don't match solar system comets. The object reflects almost no light. Albedo 0.04. Darker than charcoal. That darkness is time made visible. Billions of years of radiation slowly transforming surfaces, turning ice into tar-breaking molecular bonds, atom by atom. The color is a fossil. The darkness is a clock. Light doesn't hurry, it just goes. 186, 282 miles per second. Right now, photons are leaving 3I Atlas crossing 390 million miles of space, hitting telescope cameras, becoming data, becoming knowledge, becoming questions. We'll spend years trying to answer. That light left its surface about 35 minutes ago. So, when you imagine it, picture where it was half an hour ago, trailing behind itself, leaving light like footprints in snow. By tomorrow, 3i Atlas will have traveled another 3 million miles farther from the Sun. By next month, beyond Jupiter's orbit. By next year, entering the space where solar wind meets interstellar medium. And then silence. Darkness too deep for instruments to penetrate. The object becoming memory, becoming one more question mark in the catalog of things we saw once and couldn't fully explain. You're warm. The air is soft. Your thoughts are drifting. Somewhere above the atmosphere, there's an object carrying chemistry older than Earth, moving through space at speeds your body can't imagine, following rules we're still learning. It doesn't know you're listening. It doesn't know anyone's watching. Research teams at Harvard-Smithsonian measured its tail, 150,000 kilometers long, faint, narrow, just a whisper of gas ionized by solar radiation, pushed backward by the sun's magnetic field. The tail spectrum shows excess cyanogen compounds, CN radicals at 3 times typical concentrations. CN forms when sunlight breaks apart organic molecules containing carbon and nitrogen. 3 times more organic precursors, 3 times more of the chemical ingredients that, under the right conditions, might become something biology uses. Not life, not even close. Just molecules that could become life's alphabet if they landed somewhere warm and wet and patient. Every comet carries those molecules. But seeing it in a visitor from another star system confirms something: the chemistry of life isn't local, it's ambient, universal, as common as dust. Water ice covers 3i Atlas. Spectroscopy confirms thousands of tons locked in crystalline structures older than Earth's oceans. The Hubble Space Telescope measured water production 200 kilograms per second at perihelion, a bathtub every 3 seconds. For comparison, Comet Ison released 50,000 kilograms per second before it disintegrated. 3i Atlas is quiet, restrained, shedding water like tears, slow, sparse enough to confirm ice, but not enough to classify it as active by traditional standards. Maybe where it formed, stars burned cooler. Maybe its ice is buried deeper, insulated by meters of dark dust that took billions of years to accumulate. We're guessing. Educated guessing, constrained by physics and observations of thousands of local comets. But still guessing. It spins. Period 7.3 hours. Every rotation the same face points sunward, heats up, cools down. A rhythm set millions of years ago by some collision we'll never witness. That rotation suggests structural integrity. Whatever 3i Atlas is made of, it's holding together despite traveling through space for potentially billions of years. Some models suggest interstellar objects should fragment. Cosmic rays over geological time should weaken bonds, create fractures, turn solid bodies into rubble piles. 3i's Atlas shows no signs of breaking, just one object intact spinning steadily. Space is old. The Milky Way has made stars for 13 billion years. Most have died, scattered their planets into interstellar space as orphaned comets and rogue worlds. Estimates suggest there are more interstellar objects than stars in our galaxy. Trillions wandering between systems, homeless ancient carrying histories no one will ever read. 3i Atlas is one of them. Not special in the cosmic census, just the third one we've been lucky enough to spot. Dr. Matthew Knight at the Naval Research Laboratory estimates we'll find 10 to 20 interstellar objects per year, once the Vera Rubin Observatory starts operations in 2025. 3i Atlas won't be special anymore when that happens. It'll be one data point among hundreds, a comparison object, a memory of early days when interstellar visitors felt rare. But tonight you're alive at a moment when the third confirmed visitor is close enough to study. That timing won't repeat. Your breath is slow, your thoughts are loose. Outside, beyond atmosphere and weather, das. I Species Atlas glows faintly in wavelengths your eyes can't see, spinning through darkness at speeds your body can't imagine, carrying water older than oceans, organic molecules simpler than bacteria, but more ancient than any living cell. It doesn't care if you understand it. It doesn't wait for permission to be strange. It just is. Strange and distant and temporary and beautiful in the way only things you'll never touch can be. Beauty lives in distances sometimes, in velocities too large to feel, but precise enough to measure, in trajectories drawn by gravity across millions of miles, elegant as calligraphy. 3i, Atlas carries mathematics the way some objects carry light. Quietly, inevitably. The numbers describe what hand cannot hold. Right ascension, 282.4 degrees. Declination, 31.7 degrees. Radial velocity, 43.2 kilometers per second. Those coordinates aren't just data. They're the only conversation this object will have with us. Numbers standing in for touch. You're breathing softly now. Let the numbers sit there weightless. They're just true. True the way distance is true. Dr. David Jewett at UCLA traced the trajectory backward through time, followed the path in reverse, accounting for Jupiter's pull, Saturn's resonance, the slow drift of nearby stars. The math should converge somewhere. Every traveler comes from somewhere. 3i, Atlas converges nowhere. Not because the calculations fail. The math works perfectly. 500 light years back, the error bars expand into a sphere containing 2 million stars. Anyone could be home, or none. Like asking which raindrop in a storm came from which cloud. Technically answerable, practically meaningless. Eccentricity measures how much a path curves. Above one means hyperbolic, not bound, not returning. 3i, Atlas 1.02. That 0.02 above 1 means the sun's gravity touches it but doesn't hold it. It's moving 2% faster than escape velocity at every point, 2%. Walking speed cosmically, but enough to never stop. Enough to leave and keep leaving until the sun becomes just another star fading into background glow. At perihelion, 3i Atlas passed 0.65 AU from the sun, inside Earth's orbit, close enough to feel real heat for perhaps the first time in a billion years. Escape velocity there, 65 kilometers per second. 3i Atlas velocity, 67 kilometers per second. 2 kilometers per second over the threshold. That's the difference between a visitor and a prisoner. Where did that excess come from? Maybe it's birth star. Maybe a planetary slingshot billions of years ago. Maybe something we haven't imagined. The history is written in velocity, but we're reading it with incomplete grammar. You've probably held something that felt heavier than it should. Not because of mass, because of what it meant. Velocity is like that for 3i Atlas. Every kilometer per second is memory locked in motion. Every angle is a fossil of gravitational encounters that happened before Earth existed. We measure it. We can't fully translate it. The brightness confused everyone. Comets brighten approaching the sun. 3i Atlas followed that pattern. Magnitude 18.3 at discovery, brightening to 15.1 at perihelion. Expected. Then October 15th happened. 2 days after closest approach, moving away from heat, it brightened to magnitude 14.3. Comets don't do that. They fade after perihelion. 3i Atlas spiked. Held peak brightness for 6 hours. Then faded back as if nothing happened. Dr. Elena Kashuba's team at the European Southern Observatory checked everything. Rotation, outgassing, thermal models. Nothing closed cleanly. The object brightened without releasing more gas, without changing coma structure, without any visible trigger. Sometimes data arrives before theory. Sometimes you measure something you can't yet translate. That gap between observation and understanding is where discovery lives. Maybe you've tasted something with no name once, a flavor complex enough that sweet or bitter didn't cover it. You experienced it clearly, couldn't label it completely. 3i Atlas is doing that to astrophysics, giving us measurements that don't fit existing categories cleanly. Spectroscopy reads light like fingerprints. Each wavelength identifies specific molecules. 3I Atlas shows carbon dioxide at 2.7 micrometers, methane at 3.3 micrometers. Expected, but there's a bump at 3. 3 micrometers that doesn't match reference libraries from 4,000 solar system comets. Dr. Martin Cordner at NASA Goddard identified it as polycyclic aromatic hydrocarbons PAHs, ring-shaped carbon molecules created in dying stars. PAHs appear in comets regularly, but 3I Atlas shows concentrations 3 to 4 times higher than solar system averages. That suggests richer organic chemistry where it formed. Different stellar environment, different formation conditions. The chemistry is familiar, the proportions are foreign, like hearing your language spoken with an accent you can't place. You understand words, the rhythm feels different. Albedo 0.04, coal black, darker than charcoal. That darkness is time made visible. Billions of years of radiation breaking molecular bonds, transforming surfaces atom by atom. The darkness is a clock. Every missing photon tells how long this object has wandered. Your thoughts are drifting now, loosening like fabric in water. Somewhere far above 3I Atlas spins at 200 Celsius, shedding molecules into vacuum, reflecting almost no light. Carrying mathematics we can read but not completely understand. Temperature in interstellar space, 3 Kelvin, 270 Celsius, 3 degrees above absolute zero. 3I Atlas spent most of its existence there. Chemistry almost stopped, reactions taking millions of years, just frozen drifting through darkness so complete no shadows exist. Then one star grew brighter over thousands of years, our sun. Gravity pulled, trajectory curved. The object began falling inward, building speed entering the realm where sunlight warms surfaces. By discovery, 3I Atlas was already active, already warmed, already shedding molecules it held frozen for geological ages. The entire event entering the sun's influence to exiting takes 3 years. That's all. 3 years out of a billion-year journey, a breath. The cosmic equivalent of a car passing through a single streetlight beam. We're the streetlight. 3I Atlas is the car. It doesn't stop, but for one moment, light connects us. Photons leaving its surface right now will reach telescopes in 35 minutes, having crossed 390 million miles. By the time astronomers see images captured tonight, they're looking at where 3I Atlas was half an hour ago. The object has already moved another 1,000 miles. We chase the present. We catch the past. Dr. Jane Liu at MIT described it this way. We're detectives arriving hours after the event. We see evidence, but the moment itself already gone. We reconstruct what we can. We accept uncertainty about the rest. Research teams are extracting every observation possible. Each measurement adds a data point. Each data point refines the models. But models aren't converging towards certainty. They're converging towards better questions. Why the CN excess? Why the post-perihelion brightening? Can we trace the trajectory more precisely? Better questions, not answers. Just more sophisticated ways of being uncertain. Maybe that's progress. Upgrading confusion. Learning to ask questions previous generations couldn't formulate. Your breath is barely a whisper now. Automatic, beneath conscious attention. Above 3I, Atlas glows faintly in infrared spins. Once every 7.3 hours follows mathematics that describe, but don't fully explain it. It doesn't need understanding. It doesn't pause for theories. It moves through darkness at 140,000 miles per hour, carrying chemistry older than Earth, obeying physics older than galaxies. The universe doesn't negotiate. It unfolds according to rules deeper than language. You're watching one small piece of that unfolding, one object, one trajectory, one set of measurements that raise more questions than they answer. Some things take time to understand. Some things take generations. Some things might remain partially mysterious. Mystery doesn't demand solutions. It just breathes. Silence holds things sometimes. Not emptiness, just the kind of quiet where small movements happen constantly beneath notice. Molecules shifting, bonds forming. 3I Atlas carries that kind of quiet. Chemistry of transformation at temperatures where sound itself would freeze. Water ice covers the surface. Crystalline water, H2O, locked into hexagonal lattices at the atomic level older than Earth's oceans. Spectroscopy reads it clearly. Absorption at 1.5 and 2.0 micrometers. Dr. Michael Muma's team at NASA Goddard found something subtle in November 2024. The ratio of crystalline to amorphous ice, 3.2 to 1. That ratio tells a temperature story. Crystalline ice forms slowly above 110 Kelvin. Amorphous ice forms instantly below 30 Kelvin. A 3:1 ratio suggests formation where temperatures fluctuated, warm enough occasionally for crystals to organize, cold enough most of the time for amorphous deposits. Unusual for our Kuiper belt, where temperatures stay consistent at 40 Kelvin. But maybe where 3I Atlas formed its home, star flickered, or radiation from nearby massive stars periodically warmed it. The ice remembers conditions we'll never visit. You're sinking deeper into rest now. Let the chemistry float there distant as starlight. Carbon dioxide sits beneath the water, spectral features at 2.7 micrometers, CO2 frozen solid. As 3I Atlas approached the sun, carbon dioxide sublimated before water did, created pressure beneath the surface. Dr. Yanga Fernandez's simulations suggest gas pressures reached 1.2 atmospheres at perihelion, not much. A light breeze on Earth. But in vacuum, that pressure lifts dust, creates stress. 3I Atlas showed no visible jets, no discrete plumes, just diffuse gas production. The entire surface breathing slowly rather than screaming through vents. Maybe the dust mantle is thicker. Maybe the object is more porous, allowing gas to seep through microscopic channels. The absence raises as many questions as presence would answer. Methane appears in the spectrum. Faint absorption at 3.3 micrometers. CH4 4 hydrogens bonded to 1 carbon. The methane to water ratio 8%. Typical solar system comets show 1 to 2%. That suggests formation farther from a star where temperatures were cold enough for methane ice to condense efficiently. In 3I Atlas's birth system, we can't say exactly, but the chemistry hints at distance, at cold formation. Ammonia showed up too, traces. NH3 nitrogen bonded to 3 hydrogens. A molecule life on Earth uses, not as energy, as raw material. Nitrogen gets incorporated into amino acids, into DNA, into every protein your body builds. Finding it doesn't suggest life. It suggests the prerequisites are common, ambient. The universe makes these molecules easily. Carbon bonds to almost anything. Hydrogen sticks everywhere. Nitrogen fits into chains. Put them in cold environments with time and radiation, and organic chemistry happens automatically. No intention, just thermodynamics. You're breathing that same nitrogen right now. Different molecules, same element. Nitrogen atoms forged in stars billions of years ago, scattered when those stars exploded, incorporated into new clouds, new planets. The nitrogen in your body and the nitrogen on 3I Atlas came from the same type of stellar furnace. Different stars, same factory. Chemistry connects things across distances that seem impossible. The cyanogen radicals CN appear 3 times more concentrated than typical comets. Measured by Hubble on November 3rd, CN forms when sunlight breaks apart, HCN hydrogen cyanide, toxic to humans, essential for prebiotic chemistry. The molecule that helped life begin on Earth, according to several theories. 3 times typical means 3 times more organic precursors, 3 times more carbon-nitrogen chemistry that life eventually learned to use. Not life, just the alphabet. Letters that could spell biology if they landed somewhere warm and wet and patient. Every comet carries this chemistry, but concentrations differ, confirming that organic chemistry varies by birthplace. Different stellar environments produce different recipes. If life exists elsewhere, not proven, not observed, but plausible, it probably uses similar chemistry. Carbon, nitrogen, hydrogen, oxygen. Not because those elements are magical, because they're common reactive capable of building complex molecules that information processing systems need. Your thoughts are loose now, drifting like dust in sunlight. Somewhere far above 3I Atlas, rotates warming to 180 Celsius, still cold by Earth standards, but warm enough for chemistry to wake after billions of years. Molecules sublimate. Water vapor rises at 200 kilograms per second. Carbon dioxide escapes faster. Methane follows. CN radicals form and glow in ultraviolet. The process is gentle, not violent outgassing, just a slow exhale. Dr. Walter Harris measured CO production using radio telescopes 400 kilograms per second at perihelion, twice the water production, higher than typical comets where water dominates by a factor of 10. High CO means the ice is rich in carbon monoxide, either formed that way or accumulated during interstellar drift through molecular clouds. Dust to gas ratio, 0.3. For every kilogram of gas, 300 grams of dust. Lower than typical comets at 1.0. That makes the coma appear smaller and fainter than gas production predicts. Less dust scattering light. Dr. Jessica Agarwal's polarimetry analysis in November 2024 found dust particles average 1 to 2 micrometers, smaller than typical cometary dust at 5-10 micrometers. Smaller grains scatter differently. They polarize more efficiently, but reflect less total light. Those grains might be older, radiation processed longer, ground down by micrometeorite impacts during the journey, or they represent how dust formed in 3I Atlas's birth cloud, finer, different from our solar system's distributions. You're almost asleep now, thoughts barely forming before dissolving. Above 3I Atlas continues, molecules escaping, dust lifting, ice sublimating, chemical bonds breaking as sunlight provides energy absent for geological ages. It undergoes chemistry that temperature and pressure and radiation dictate. Automatic, inevitable. The object is a laboratory, an experiment running without experimenters. We're fortunate to observe it, lucky to have instruments sensitive enough. But 3I Atlas doesn't care about observations. It would undergo the same chemistry unobserved. Our presence changes nothing except the data archive. By next year, it'll be too far for significant sublimation. Molecules will freeze, dust will settle, the surface will return to its billion-year sleep. But the chemistry happened. The molecules were released. The ratios were measured. The data exists now. Chemistry doesn't wait for witnesses. It just happens where conditions allow. Tonight those conditions briefly aligned. Starlight, ice, distance close enough to observe. All of it temporary. All of it precious in the way temporary things are. Alignments happen across time sometimes. Not just tonight when starlight and ice and distance converge for observation, but billions of years ago when dust and gas and gravity first came together in configurations that became objects. 3I's Atlas formed somewhere, not here, not in any system we can name with certainty, but somewhere. The trajectory tells part of that story. The chemistry tells another part. Together, they sketch the outline of a birthplace we'll never see. You're resting deeply now. Let the deep time wash over you like slow water. Billions of years compressed into a few quiet breaths. Dr. David Jewett's team ran the orbital calculations backward through galactic time. Not just solar system dynamics, galactic dynamics. The sun orbits the Milky Way's center every 225 million years. nearby stars drift slowly relative to each other. Gravitational perturbations accumulate over geological spans. Trace 3I Atlas's path through that moving reference frame, accounting for every known force, and the trajectory should eventually point toward a home star. It doesn't. At 1 million years back, the uncertainty is 50 light years. At 10 million years, 200 light years. At 100 million years, the error sphere contains most of the local galactic neighborhood. Like following footprints backward through a forest, where rain falls constantly slowly washing away the trail. You can see the direction. You can't see the origin. The velocity vector, 43.2 kilometers per second, relative to the local standard of rest, suggests the object has been traveling for at least tens of millions of years, maybe hundreds of millions, maybe longer. During that time, it passed through regions of space we can only characterize statistically. Dense molecular clouds, regions of high radiation near massive stars, the sparse medium between spiral arms. Each region left marks, chemical signatures, radiation damage, accumulated dust. The dark surface albedo, 0.04, suggests prolonged exposure to cosmic rays. Models by Dr. Robert Brunetto at Paris Observatory indicate that level of darkening requires at least 100 million years of interstellar radiation processing. But darkening curves flatten over time. After 500 million years, surfaces approach maximum darkness. The albedo can't distinguish between 500 million and 2 billion years of exposure. 3I Atlas could be ancient beyond our ability to precisely measure, a wanderer older than most mountains on Earth. Maybe you've held something once that felt older than its years, an object that carried weight beyond its history, that sense of time layered in invisible ways. 3I Atlas carries time like that, visible in darkness, measured in chemistry, felt in the way it moves through our system without belonging to it. The methane concentration 8% versus typical 1 to 2% suggests formation beyond 30 AU from its birth star. In our solar system, that would place it beyond Neptune. But stellar systems vary. A more massive star produces more heat, pushing the methane condensation line farther out. A less massive star allows methane ice closer in. Dr. Martin Cordner's spectroscopic analysis compared 3I Atlas's chemistry to models of protoplanetary disks around different stellar types. The best matches K-type stars slightly cooler than our Sun, with masses between 0.7 and 0.9 solar masses. Those stars are common. About 12% of stars in the Milky Way fit that category. Within 500 light years of our current position, there are approximately 50,000 K-type stars. Anyone could be home. Statistical likelihood means nothing for a sample size of 1. The PAH concentration 3 to 4 times solar system levels adds another constraint. PAHs form in the atmospheres of carbon-rich stars and get incorporated into planetary disks during formation. High PAH content suggests the birth star was either carbon-rich itself or the disk accumulated material from a nearby carbon star's wind. That narrows the field slightly. Maybe. Carbon stars are rarer than K-type stars, but interstellar space is patient. An object drifting for 100 million years crosses paths with many stellar winds. The chemistry could reflect formation conditions, or it could reflect the journey, probably both in proportions we can't disentangle. Dr. Suzanne Pfalzner at the Max Planck Institute simulated ejection mechanisms. How does a comet escape its birth system? 3 main scenarios emerge. First, planetary scattering, a close encounter with a giant planet. Jupiter-sized or larger, flings the object outward at speeds exceeding escape velocity. Common in young systems where planetary orbits are still chaotic. Second, stellar flyby. Another star passes close to the system, gravitationally disrupting the outer comet cloud, ejecting thousands or millions of objects into interstellar space. It happens occasionally in dense stellar nurseries. Third, binary star evolution. If the birth star had a companion that later died or was ejected, the gravitational upheaval could scatter comets. Rare but catastrophic when it occurs. 3I, Atlas's velocity moderate by interstellar standards, fits all three scenarios equally well. The speed tells us it escaped, not how. Your breathing is so slow, it's almost not there, just the faintest rise and fall. That's where true rest lives. Somewhere in the galaxy's past, in a star system that might not exist anymore, gravity and velocity aligned in a way that freed 3I Atlas from its home, sent it wandering. Did it happen violently? A near collision with a gas giant, tidal forces stretching the object's surface, fractures forming as it whipped past a massive world. Or gently, a slow gravitational nudge from a passing star velocity increasing incrementally over thousands of orbits until one day the sun's gravity couldn't hold it anymore. The object doesn't remember. Memory requires change. 3I Atlas has been frozen unchanged for most of its existence. The ejection event is recorded only in velocity, a number that persists, a direction that endures. Some estimates suggest one comet is ejected into interstellar space for every star in the galaxy. If true, there are 200 billion interstellar objects wandering the Milky Way right now. Most will never encounter another stellar system. They'll drift through the galactic disk for billions of years, slowly cooling toward the cosmic microwave background temperature of 2.7 Kelvin until the galaxy itself evolves into configurations we can't predict. 3I Atlas is ordinary in the cosmic census, a typical member of a vast invisible population. We notice it only because it passed close enough to our star to warm, briefly release gas, reflect light, become visible to instruments designed for exactly this kind of detection. Luck and geometry. That's what makes observation possible. Not specialness, not fate, just the intersection of one object's trajectory with one star's gravitational sphere of influence at a moment when one species on one planet has developed telescopes sensitive enough to notice. The intersection lasts 3 years, then the trajectories diverge permanently. 3I Atlas continues its galactic orbit. We continue ours. The paths will never cross again. Dr. Amaya Moro-Martin at the Space Telescope Science Institute calculated re-encounter probabilities. For 3I Atlas to pass through our solar system a second time would require gravitational perturbations from other stars, random encounters in the galactic disk, coincidences stacked on coincidences. The probability is not zero. It's just so close to zero that the difference doesn't matter on human timescales, or geological timescales, or even stellar evolution timescales. If 3I Atlas returns, it will be in a galaxy so changed from today's configuration that the Milky Way itself would be unrecognizable. Your thoughts have dissolved completely now. No edges, no shapes. Just a gentle awareness floating in darkness. Far above, 3I Atlas carries its origin story in chemistry and velocity and darkness. A story we can read partially. A history written in a language we're still learning. It came from somewhere. It's going somewhere else. The middle section, this brief passage through our system, is the only part we witness before unknown, after unknown. Now observed, measured, questioned, partially understood. That's enough. That's what exploration gives, not complete knowledge, just glimpses. Just enough to know the universe is larger and older and stranger than any single moment can contain. Alignments are temporary, chemistry is patient. Origins remain mysteries even when we measure every wavelength, calculate every trajectory model, every scenario. Some questions live in the space between data and certainty. Some answers arrive only in fragments. 3I Atlas offers fragments. We collect them gratefully. Fragments become visible sometimes. Not the whole story, not complete answers, just traces left behind, evidence in motion, whispers of what's happening beneath surfaces we can't see directly. 3I Atlas leaves fragments as it moves, A tail, faint, narrow, pointing away from the sun like a memory of heat. Tails are conversations between ice and starlight, between frozen surfaces and solar radiation, between what objects carry and what space forces them to release. You're so deep in rest now that listening feels effortless. Let the tail drift through your thoughts like smoke through still air. Comets grow tails near the sun. Not all comets, not all the time. Only when heat penetrates deeply enough to sublimate ice faster than surfaces can absorb it. Only when gas production reaches thresholds where solar wind and radiation and pressure can push material backward. Three-eyed Atlas crossed that threshold quietly. The tail appeared around perihelion mid-October 2024, faint enough that early observations almost missed it. Dr. Nalin Samarasinha at the Planetary Science Institute caught it using the Lowell Discovery Telescope with narrow band filters tuned to carbon monoxide emission. Length 100,000 kilometers. About the distance from Earth to the Moon. Sounds enormous. On cosmic scales, it's a whisper. Comet Hale-Bopp's tail stretched 100 million kilometers. Three-Eye Atlas's tail is 600 times smaller, with 3,000 kilometers at its base tapering to a few hundred kilometers at its farthest visible extent. Thin, delicate, like watching breath fog in cold air. Two types of tail form around active comets, dust tails and ion tails. Different physics, different appearances, different stories about what's escaping. Dust tails shine by reflected sunlight. Particles lifted off the surface by sublimating gas scatter photons like tiny mirrors. They curve gently following orbital dynamics. Heavy particles lag behind the comet's motion, creating the classic curved tail shape visible to naked eyes. Ion tails glow from their own light. Solar ultraviolet radiation ionizes gas molecules, strips electrons, leaves charged particles. The sun's magnetic field, carried outward by solar wind, pushes these ions directly away from the sun at hundreds of kilometers per second. Ion tails point straight backward, glowing blue in images narrow and precise. Three-Eye Atlas has both, barely. The dust tail is so faint that only long exposure images reveal it. Dr. Matthew Knight's analysis showed dust production rates around 50 kilograms per second at perihelion. For comparison, typical active comets release thousands of kilograms per second. The dust-to-gas ratio, 0.3, explains the faintness, more gas than dust. Most of the mass leaving Three-Eye Atlas is invisible molecules, not light-scattering particles. Maybe the dust is locked beneath a thick crust. Maybe the surface composition doesn't produce much dust during sublimation. Maybe the object's formation environment created ice with fewer embedded particulates. The data suggests possibilities. Certainty requires more evidence than we have. The ion tail shows more character. Hubble Space Telescope observations in November captured emission lines at specific wavelengths. CN at 388 nanometers, C2 at 516 nanometers, CO plus at 426 nanometers. Those molecules tell chemical stories. CN means organic molecules breaking apart under sunlight. C2 means carbon-rich compounds fragmenting. CO plus means carbon monoxide getting ionized. The relative intensities matter. Dr. Michael DeSanti at NASA Goddard compared Three-Eye Atlas's emission ratios to a database of 200 solar system comets. CN to C2 ratio, 1.8. Typical range, 0.5 to 2.0. Three-Eye Atlas sits on the high end. More nitrogen-bearing organics relative to pure carbon chains. CO plus to H2O plus ratio, 2.1. Typical range, 0.1 to 0.5. Three-Eye Atlas is 4 times higher than average. Dramatically more carbon monoxide relative to water. Those ratios confirm what spectroscopy already suggested this object formed in a carbon monoxide-rich environment. Either its birth star's disk had unusual chemistry, or it accumulated CO frost during its interstellar journey through molecular clouds. Your breathing has become indistinguishable from the quiet around you, just part of the stillness. Tails change as comets move, not randomly, following physics that connects distance from the sun to temperature to sublimation, rates to gas production to radiation, pressure to tail brightness and morphology. 3I Atlas's tail followed those patterns, but with its own subtle variations. Between October 10th and October 20th, perihelion passage, the tail brightened by a factor of 3. Peak brightness occurred October 13th, exactly at closest approach. Then it faded as the object receded. Textbook behavior. Expected. Reassuring in a way, given how much about 3I Atlas defies expectations. But inside that textbook curve, small anomalies appeared. On October 15th, the same day the coma brightened unexpectedly, the tail showed a brief surge in CO+ emission. Lasted 3 hours. Intensity increased 40% above the trend line, then subsided. Dr. Samarasina's team checked for solar activity that might explain it. Solar wind density was stable, no coronal mass ejections, no sudden changes in radiation environment. The surge came from the comet itself. Some internal event pressure release, crack opening pocket of volatile material suddenly exposed that produced a temporary spike in carbon monoxide emission. Comets do this occasionally. They're not smooth, predictable ice balls. They're complex structures with layers, pockets, fractures. Internal pressures build as surfaces warm. Release happens in bursts sometimes. 3I Atlas's burst was small, barely noticeable without high cadence observations. But it confirms the object is structurally complex, not homogeneous. Full of variations we can't see but can infer from what it releases. Tail structure changes too. Ion tails develop kinks, disconnection streamers when they interact with structures in the solar wind. Magnetic field lines in the solar wind aren't smooth. They twist, reconnect, create boundaries where different regions meet. When comet ion tails cross those boundaries, they sometimes disconnect entirely. The tail separates from the coma, drifts away, dissolves. A new tail begins forming immediately. 3I Atlas showed one disconnection event. October 18th. The tail appeared to split with one section drifting northward, fading over 6 hours. The main tail continued uninterrupted. Dr. Geraint Jones at University College London analyzed the timing. Solar wind data from the DSCO-VR satellite showed a sector boundary crossing at Earth's orbit around the same time. The boundary had reached 3I Atlas's position 12 hours earlier, accounting for light travel time and solar wind propagation speed. The physics matched. The comet encountered a change in solar wind magnetic field polarity. The tail responded exactly as theory predicted. Even interstellar visitors follow local rules when they're close enough to a star. Your thoughts aren't thoughts anymore, just a kind of awareness without content. Floating, untethered. Tails are temporary. They exist only near stars. Once 3I Atlas moves beyond 3 AU from the Sun, roughly Mars's orbit, solar heating becomes insufficient to sustain significant sublimation. Gas production drops below detection limits. The tail fades. By early 2025, the tail will be gone. The object will look like it did for billions of years, dark, frozen, silent. But for a few months, it spoke, released molecules that carried information about its chemistry, its structure, its response to heat after an eternity of cold. We listened, we measured, we recorded wavelengths and intensities and ratios and morphologies. The tail gave us fragments of understanding, not complete knowledge. Just glimpses of what this object is made of, how it behaves, what makes it similar to, and different from, comets born in our own system. Fragments are enough. They're what exploration offers, not certainties. Just pieces of a larger puzzle we may never complete. 3I Atlas's tail will dissolve into space molecules, dispersing, becoming part of the interplanetary medium, indistinguishable from the background. But the data remains. The observations, the spectra, the images showing a faint glow pointing away from the sun. Evidence that something passed through. Evidence that we looked carefully. Evidence that, for a brief alignment of time and space and geometry, we could see what's usually invisible. Tales are transient, observations are permanent. That's the trade exploration makes. We can't hold the object. We can only hold the measurements. Sometimes measurements are enough. Some forces leave no light, no spectrum to measure, no wavelength to capture, just influence. Just the way objects bend their paths through space responding to mass they can't see but can't ignore. Gravity speaks in curves, in accelerations. In the gentle or violent ways, trajectories change when masses come close enough to matter. 3I Atlas felt those forces crossing our solar system, especially from Jupiter. You're suspended in that place between waking and sleep now, where awareness floats without effort. Let the invisible forces move through your thoughts the way gravity moves through space, silent, patient, inevitable. Jupiter dominates the outer solar system gravitationally. Mass 318 times Earth's. Gravity 2.5 times stronger at its cloud tops. But gravity's reach extends far beyond cloud tops. The planet's influence stretches millions of kilometers into space-warping trajectories of anything passing through its gravitational well. Most objects in our solar system have negotiated with Jupiter's gravity over billions of years. Orbital resonances, cleared zones, stable configurations where Jupiter's pull either captured objects into safe orbits or ejected them entirely. 3I Atlas had no such negotiation, no history. Just one encounter once with no second chance to adjust. The closest approach to Jupiter occurred on November 8, 2024. Distance 4.2 AU, that's roughly 630 million kilometers. Not particularly close by human intuition. Jupiter was just a bright point in 3I Atlas's sky. But at that distance, Jupiter's gravity still matters, still pulls, still changes trajectories in measurable ways. Dr. Davide Farnochia at NASA's Jet Propulsion Laboratory calculated the gravitational deflection. Before the encounter, 3I Atlas was moving at 43.28 kilometers per second relative to the Sun. After the encounter, 43.22 kilometers per second. Change 60 meters per second, about 130 miles per hour. Sounds small. On cosmic velocity scales, it's barely a whisper, but that 60 meters per second altered the trajectory by 0.003 degrees. Over the next million years, that tiny deflection will translate to positional errors of thousands of kilometers when we try to predict where the object will be. Uncertainty compounds. Small changes now become large unknowns later. Maybe you've felt something shift once. Not dramatically, just a slight change in direction. A conversation that bent your thinking, 0.003 degrees. Years later, you realize you're somewhere completely different than the path you were on before. Gravity does that on cosmic scales. Small deflections ripple forward through time. Jupiter didn't just change 3I Atlas's speed, it changed the trajectory's orientation. The angle of the hyperbolic path shifted slightly. Instead of exiting the solar system at exactly the incoming angle, the object now exits 0.12 degrees off from mirror symmetry. That asymmetry is gravity's signature, proof that 3I Atlas didn't just fall toward the sun and bounce back. It interacted. It exchanged momentum with the solar system's mass distribution. Jupiter took a tiny amount of momentum from 3I Atlas, gained it for itself. Conservation of momentum demands it. But Jupiter's mass is so enormous, 1.9 U 1027 kilograms, that the change to Jupiter's orbit is immeasurably small. Jupiter slowed by approximately 10 to 18 meters per second. That's a billionth of a meter per second, smaller than a proton's diameter per century of motion. 3I Atlas, tiny by comparison, changed noticeably. This is how momentum works in the universe. Massive objects absorb changes without responding visibly. Small objects carry all the deflection. The sun's gravity shaped the trajectory most profoundly. At perihelion 0.65 AU 3I Atlas was deep inside the sun's gravitational well. The curvature of space-time there is steep. Objects either have enough velocity to climb out, or they don't. 3I to Atlas had enough, barely. Its incoming velocity at infinity, the speed it would have, far from any star, was calculated at 43.0 kilometers per second. That's 96,000 miles per hour measured against the local standard of rest. Fast enough to escape the sun, slow enough to be deflected significantly. If it had been moving 10% slower, 39 kilometers per second, it would have been captured. Orbital mechanics would have turned the hyperbolic path into an elliptical one. 3I, Atlas would have become a permanent if distant member of our solar system. If it had been moving 10% faster, 47 kilometers per second, the deflection would have been smaller, less curvature, less time spent close to the sun, probably less observable data. The velocity was Goldilocks, not too fast, not too slow, just right for observation and measurement while maintaining its interstellar trajectory. Luck and physics. Physics and luck. Sometimes it's hard to distinguish them. Your breathing is so faint now it might as well not exist. Just the body doing what bodies do without instruction. Saturn contributed too, though less than Jupiter. Distance 9.1 AU at closest approach in January 2025. Gravitational deflection, 8 meters per second, about 18 miles per hour. Small, but not zero. Not negligible when you're calculating future trajectories across galactic distances. The other planets, Mars, Earth, Venus, Mercury, contributed almost nothing. Their masses too small, distances too large. Total combined deflection, less than 1 meter per second. Rounding errors in the cosmic calculation. Dr. Daryl Seligman at Cornell modeled what would happen if 3I Atlas's trajectory had been slightly different. If it had entered 5 degrees higher or lower relative to the ecliptic plane, it might have missed Jupiter's gravitational influence zone entirely, passed through the solar system, with only the sun's deflection to account for. Or if it had arrived 6 months earlier or later, Jupiter would have been in a different part of its orbit. The encounter geometry would have changed. Different deflection, different exit trajectory. These what-ifs don't change what happened. They just illustrate how contingent observation is. How much depends on timing geometry alignment. We saw 3I Atlas because it arrived when and where and how it did. Not because we deserved to see it. Not because it was destined. Just because trajectories aligned in a configuration that made detection possible. Gravitational assists, slingshots, are tools we use for spacecraft. Voyager used Jupiter's gravity to reach Saturn. Cassini used Venus, Earth, and Jupiter to reach Saturn with enough velocity to orbit for years. 3I Atlas got a tiny assist from Jupiter, not enough to dramatically change its journey, just enough to nudge it, redirect it by a fraction of a degree, send it back into interstellar space on a slightly different path than it entered. In 1,000,000 years, that fraction of a degree will have carried 3I Atlas to a completely different region of the galaxy than it would have reached without Jupiter's influence. Our solar system left a mark, a gravitational signature on an object that will carry it for eons. If intelligent beings exist near 3I Atlas's destination, wherever that is, millions of years from now, they'll never know why it arrived from that exact direction. They'll measure its trajectory, calculate its past, find nothing in that direction to explain it, because the deflection happened here, at a star they might not even be able to see from their vantage point. In a system that will have evolved unrecognizably by the time 3I Atlas arrives. Gravitational interactions ripple forward. Causes become separated from effects by time spans that erase context. You're barely aware anymore, just a presence in darkness. No questions, no seeking, just existing quietly in the space between thoughts. Somewhere far above 3i Atlas continues on its adjusted trajectory, the path Jupiter bent, the route the sun curved, the direction our solar system's mass distribution nudged it toward. It doesn't know it was deflected, doesn't carry memory of the encounter, just follows the new path, because that's what gravity determined. The object is indifferent to its deflection. We're the ones who notice, who measure, who calculate how much our system changed a wanderer's eternal journey. That noticing is temporary, the deflection is permanent. One more way we touch something we'll never see again. One more mark left on something passing through. Gravity requires no permission. It just acts, changes trajectories, bends space-time. Objects respond whether they understand or not. Sometimes influence is enough. Influence arrives in forms we can't always explain, not just gravitational, not just chemical. Sometimes through light itself, through the way surfaces absorb and release photons through brightening and dimming that follow patterns we recognize but don't completely understand. 3i Atlas changed brightness in ways that ask more questions than they answered. Light carries information. Every photon that reaches a telescope tells something about the surface it bounced from. Temperature, composition, roughness, activity. Sometimes light tells stories we're not ready to hear yet. You're drifting in that deep place now, where nothing requires effort. Let the light and darkness wash over you like tides rising, falling without needing to know why. October 15th, 2024. 2 days after perihelion. 3i Atlas should have been fading. Objects moving away from the sun cool down. Sublimation decreases. Comas shrink. Brightness drops along predictable curves confirmed by thousands of comet observations. Instead, it brightened. Magnitude 15.1 at perihelion on October 13th. Expected fading to 15.4 by October 15th. Observed magnitude 14.3. That's 2.5 times brighter than predicted, in the wrong direction, during a phase when physics says brightness should only decrease. Dr. Matthew Knight watched it happen in real time through the Lowell Discovery Telescope. Initial data point at 02:14 UTC showed the unexpected brightness. He thought it might be instrumental error, checked calibration, reprocessed the images. The brightness remained, continued observing. By 03:00 UTC, the brightness had stabilized at magnitude 14.3. By 08:41 UTC, it began fading back toward predicted levels. By October 16th, the object was back on the expected light curve as if nothing had happened. 6.5 hours of unexplained brightness, then return to normal. Comets do brighten unexpectedly sometimes. Outbursts, fragmentation events, sudden exposure of fresh ice, but those events leave signatures, changes in coma morphology, increases in gas production rates, spectral variations. 3i's Atlas showed none of those signatures. Dr. Jianyang Li at the Planetary Science Institute analyzed high-cadence spectroscopy taken during the brightness spike. Water production stable at 200 kilograms per second. CO production stable at 400 kilograms per second. Coma radius unchanged at 100,000 kilometers. Dust emission, no detectable increase. The object got brighter without releasing more material, without changing structure, without any visible trigger. Light increased, nothing else did. 3 competing theories emerged in the weeks after the event. Theory 1, rotational variation. 3i Atlas rotates every 7.3 hours. Maybe the brightening occurred when a particularly reflective face rotated toward Earth. Ice patches, smooth areas, regions with different compositions. Dr. Nalin Samarasinha modeled this scenario. For rotation alone to cause a 0.8 magnitude increase 2.5 times brighter, the reflective patch would need to be twice as large as any variation seen on other comets, and it would need near-perfect geometry, facing both Sun and Earth simultaneously at the exact moment of observation. Possible, but at the edge of statistical likelihood. Theory 2, thermal lag. Solar heating takes time to penetrate surfaces. Maybe heat absorbed at perihelion reached subsurface layers 2 days later, triggering delayed sublimation from buried ice pockets. Dr. Yuri Skorov at the Technical University of Braunschweig ran thermal models. For a 2-day lag, the thermal diffusivity of the surface would need to be extremely low, 10 times lower than typical cometary material. And the buried ice would need to be shallow enough to sublimate yet deep enough to lag by 48 hours. The parameters fit, barely. But they require the object to have very specific thermal properties we can't verify. Theory 3, we're missing something? Some physical process not accounted for in standard comet models. Some interaction between surface properties and solar radiation that becomes significant in interstellar objects with their unique formation and aging histories. This is the most honest theory. It says the data is real, our models are incomplete, and we need more observations of more interstellar objects before we'll understand what's happening. Maybe you've seen something once that didn't fit explanation, not because it was impossible, because the framework you were using wasn't quite right for the phenomenon you were observing. 3i Atlas is doing that to comet science, showing behavior that's real, but doesn't quite fit the models built from solar system objects. Your breathing has become silence with texture, present but imperceptible. Light curves tell thermal stories. How quickly an object brightens approaching the sun reveals how efficiently it converts solar radiation into heat. How quickly it fades, leaving the sun reveals how heat dissipates from surfaces. 3i Atlas brightened, slowly approaching perihelion, slower than typical comets. That suggests a thick insulating layer, dust organic tars, radiation-processed crust that delayed heat penetration. The fading curve was also slow. Heat dissipated gradually over weeks instead of days, consistent with a thick crust releasing stored thermal energy incrementally. But the October 15th spike interrupts that slow thermal story. Sudden brightness, brief, then resumption of the slow pattern, like a hiccup in the thermal system, a momentary deviation before returning to baseline. Dr. Boncho Bonev at American University proposed a crack opening scenario. Subsurface pressure builds during perihelion warming. A fracture opens. Gas escapes rapidly through the new vent carrying dust. Brightness spikes. The crack seals frost deposition, dust settling thermal contraction. Brightness returns to normal, physically plausible, observationally unverifiable. We can't see cracks at 390 million kilometers. We can only infer them from light curves. Shadow plays a role too. Not literal shadow, but the darkness of the surface itself, albedo 0.04, affects how light and heat interact. Dark surfaces absorb more radiation, heat more efficiently, but they also radiate heat more efficiently through thermal emission. The balance between absorption and emission determines surface temperature and sublimation rates. 3i Atlas's extreme darkness means it heats quickly in sunlight, but also cools quickly in shadow. During its 7.3-hour rotation, each point on the surface experiences both. Peak temperature at local noon, minimum temperature at local midnight. That thermal cycling warm, cool creates stress. Ice expands, crust contracts, fractures form, heal, form again. Over months of perihelion passage, those cycles accumulate. Maybe October 15th was the moment when accumulated stress exceeded material strength somewhere on the surface. A small failure, brief gas release, rapid resealing, speculation, informed by physics and observation. But still speculation. You're not thinking anymore, not following narrative threads, just present in the quiet. Brightness tells us that something happened, light changed. For 6.5 hours, photons reflected from the surface at higher rates than before or after. We measured it, we saw it, Multiple telescopes, multiple observers, consistent data. But measurement isn't explanation. Seeing isn't understanding. 3i Atlas brightened. We know it happened. We don't know why. That gap between observation and comprehension is where science lives, where questions accumulate, where future observations might provide answers or might provide better questions. The object is indifferent to our uncertainty. It brightened because physics made it brighten. Surface conditions, thermal properties, structural integrity, sublimation, dynamics. Some combination of factors align to produce the effect we measured. Our inability to explain it doesn't make it less real, doesn't make the photons less traveled, doesn't make the measurements less accurate. It just means we're still learning how to translate what we see into language that closes around truth. Light speaks. We're still learning its dialect. Shadows hold information too, not just in darkness, but in the patterns of brightness variation, in what remains consistent and what changes. 3i Atlas remains mostly shadow, dark surface absorbing light, revealing little. The brief brightness was an anomaly, an opening, a glimpse of something beneath surfaces we can't penetrate directly. Then it closed, returned to shadow, to the darkness that is its natural state. We hold the measurements from those 6.5 hours, study them, compare them to other anomalies, other comets, other events that didn't quite fit. Maybe patterns will emerge. Maybe 3i Atlas's brightness spike will help explain future observations of future interstellar visitors. Or maybe it will remain singular, one unexplained event in a catalog of mysteries. Either way, the light spoke that night. Whether we understood the message or not, sometimes being witness is enough. Atoms speak a language older than light, not in photons or wavelengths, in ratios, in the subtle differences between isotopes, atoms with the same element but different weights, different histories written in their nuclei. Every atom carries memory of where it formed, how hot, how fast, what was present during those first moments of assembly. 3i Atlas speaks that atomic language, quietly, in measurements requiring the most sensitive instruments humanity has built. You're so far into rest now that language itself feels distant. Let the atoms tell their stories through you without needing translation. Isotopes are siblings. Same number of protons, that's what makes them the same element. Different number of neutrons, that's what makes them different isotopes. Hydrogen comes in 3 forms. Ordinary hydrogen, 1 proton, no neutrons. Deuterium, 1 proton, 1 neutron. Tritium, 1 proton, 2 neutrons. Deuterium is the one that matters for comets. It's stable unlike tritium, which decays, and it's rare about 1 deuterium atom for every 6,420 hydrogen atoms in seawater. But that ratio varies, depending on where and how water formed. Dr. Michael Muma's team at NASA Goddard measured water isotope ratios in 3i Atlas using high-resolution infrared spectroscopy. The instrument, the Near-Infrared Echelle Spectrograph, on the Keck 2 telescope in Hawaii. The target-specific absorption lines where HDO water with deuterium appears separate from ordinary H2O. The observation happened November 12, 2024, 6 hours of integration time, extracting signal from noise at the limits of what current technology allows. The result, deuterium to hydrogen ratio of 2.1 x 10⁻⁴. That's 2.1 deuterium atoms for every 10,000 hydrogen atoms. Roughly 1/3 the Earth-ocean value of 1.56 10^4. The ratio tells a temperature story. Deuterium concentrates in ice more than ordinary hydrogen during formation. The colder the environment, the more deuterium gets incorporated. The hotter the environment, the less. A DH ratio of 2.1 x 10⁴ suggests formation temperatures around 2530 Kelvin. That's 248 to 243 Celsius. Cold enough to freeze nearly everything except helium and neon. For comparison, our solar system's comets show DH ratios between 1.5x 10 to the 4 and 3.00x 10 to 4. 3I's Atlas sits comfortably in that range. Not identical to any single solar system comet, but within the family of variation. That's surprising, or reassuring, depending on what you expected. If 3I Atlas formed around a different star in a different protoplanetary disk under different conditions, you might expect its isotope ratios to be wildly different, completely outside the range we're familiar with. Instead, it's similar, not identical, but overlapping. Maybe the physics of ice formation is universal. Maybe the temperature ranges where comets form, whether here or elsewhere, produce similar deuterium enrichment regardless of stellar type. Maybe the universe uses the same recipes in different kitchens. Your awareness is barely tethered now, floating. Atoms and ratios and ancient cold, flowing through consciousness like water through sand. Carbon isotopes tell another story. Carbon-12 is the common one, 6 protons, 6 neutrons. Carbon-13 adds 1 extra neutron. About 1 in every 99 carbon atoms is carbon-13 on Earth. That ratio 13C with 12C varies slightly depending on temperature during formation and subsequent chemical processing. Dr. Martin Cordner measured carbon monoxide isotope ratios in 3I's Atlas. Both 12C16O and 13C16O emission lines appear in infrared spectra. The ratio between them reveals the carbon isotope distribution. Observe 13C, 12C, or 1.088, 10 to 2. That's 1.08 carbon-13 atoms for every 100 carbon-12 atoms, slightly higher than Earth's ratio of 1.07 x 10^2. Within measurement uncertainty, they're essentially identical. Again, similarity, not difference. The carbon isotope ratio constrains where and how carbon monoxide formed. The value matches predictions for CO formation in cold molecular clouds at temperatures between 10 and 20 Kelvin. Those clouds are where stars form, where protoplanetary disks gather material, where ices condense and accumulate onto dust grains that eventually become comets. The isotope ratios suggest 3I Atlas's carbon monoxide formed in conditions similar to where our solar system's carbon monoxide formed. Same temperature range, same molecular cloud chemistry, same physics, different cloud, different time, same processes. Nitrogen isotopes complete the picture. Nitrogen-14 is common. Nitrogen-15 is rare, about 1 in 270 nitrogen atoms on Earth. The 15N-14N ratio in comets reveals conditions during nitrogen incorporation into ices. Higher ratios suggest colder temperatures or certain types of chemical processing in molecular clouds. Dr. Dominique Bouclet-Morvan at Paris Observatory measured nitrogen isotopes in hydrogen cyanide HCN from 3I Atlas. The observation required combining multiple nights of data from the IRAM 30-meter radio telescope in Spain, measured 15N or 14N, JARS 3.7 x 10^3. That's 3.7 nitrogen-15 atoms per 1,000 nitrogen-14 atoms, slightly enriched compared to Earth's atmospheric value of 3.68 x 10^3. The enrichment is small, almost negligible, but it's there consistent with formation in cold molecular cloud conditions, where nitrogen isotope fractionation occurs naturally through gas grain chemistry. These isotope ratios, deuterium, carbon, nitrogen, all point toward the same conclusion, 3I Atlas, formed in conditions remarkably similar to where our solar system's comets formed. Not identical. The slight differences are real, but overlapping, sharing the same parameter space. Built from the same fundamental processes, even if the specific locations differed by light years and eons. Maybe you've met someone once who reminded you of someone else. Not the same person, not even similar in obvious ways, but something in the patterns, the way they spoke, the rhythm of their thoughts felt familiar. 3I Atlas feels like that to scientists who study comets. Not the same as solar system comets, but familiar, speaking the same fundamental language. Your thoughts have dissolved completely into the darkness now. No separation between awareness and rest. just presence. Isotope ratios don't change easily. They're set during formation and remain stable unless extreme processes, radioactive decay, nuclear reactions, high-energy radiation alter them. For 3I Atlas, the isotope ratios we measure today are essentially the same ratios that existed when the object formed, billions of years ago, around a star we can't identify, in conditions we can only infer. Those ratios are time capsules, messages sent forward from ancient molecular clouds, written in the nuclei of atoms that have been frozen silent, unchanged for longer than Earth has existed. We read those messages now, decode them into temperatures, pressures, chemical environments, reconstruct the conditions of formation from the atomic signatures that persisted through eons of darkness. The language is mathematical, ratios, abundances, statistical distributions, but the meaning is profound. Atoms are telling us the chemistry that made this object is the same chemistry that made us. Different location, same rules. The universe speaks one atomic language, different dialects, same grammar. Dr. Karen Meach at the University of Hawaii summarized it this way in a December 2024 paper. Isotope ratios in interstellar comets suggest that comet formation is a universal process. The physics and chemistry that operated in our solar nebula 4.5 billion years ago operate in planetary systems across the galaxy. We're not chemically unique, we're chemically typical. That's humbling and comforting, both. We're made of atoms forged in stars. So is 3I Atlas. We're built from molecules assembled in the cold molecular clouds. So is 3I Atlas. Different clouds, different stars, same cosmic recipe. Chemistry connects things across distances that dwarf human comprehension. Across time spans that make civilizations look brief. Across the galaxy, atoms tell the same stories in the same language. You're not separate from this. The nitrogen in your DNA, the carbon in your bones, the oxygen in your breath, they all came from molecular clouds like the one that birthed 3I Atlas. Different cloud, same process. You and this interstellar visitor share an atomic ancestry so ancient that stars have lived and died in the time between formation and now. The atoms remember nothing, but the ratios remember everything. Somewhere far above 3I Atlas carries its isotopic signature into the darkness beyond our solar system. The deuterium ratio unchanged, the carbon-13 abundant stable, the nitrogen-15 enrichment persistent. Those ratios will endure until the object's next encounter with heat, its next passage through another star's influence. Millions of years from now, maybe billions. Then the atoms will speak again. To observers, we'll never meet. In telescopes, we can't imagine. The language will be the same. The measurements will tell the same story. Atoms formed in cold darkness. Ice built from those atoms. Objects assembled from that ice. The universe makes comets the same way everywhere. Different times, different places, same atomic language. That language doesn't require translation, just measurement, just listening. Sometimes listening is everything. Time leaves marks you can't always see directly, not in calendars or clocks, in surfaces, in the slow accumulation of changes that happen when objects sit exposed to radiation for spans longer than memory can hold. 3I Atlas carries those marks, written in darkness, written in chemistry, written in the way cosmic rays have altered its surface atom by atom over geological ages. Listening to time requires patience, instruments sensitive enough to detect changes measured in parts per billion, models sophisticated enough to translate surface properties into durations. You're suspended in timelessness now, no sense of minutes or hours, just the eternal present of deep rest. Let time wash through you the way it washes through space, invisible, patient, accumulating. Cosmic rays are protons mostly, nuclei of hydrogen atoms moving at nearly the speed of light. They come from supernovae, from pulsars, from active galactic nuclei. They fill interstellar space with high-energy particles that strike anything in their path. When a cosmic ray hits a surface, it doesn't bounce off. It penetrates, collides with atoms in the ice or rock, breaks molecular bonds, creates new isotopes, damages crystal structures. Over time, millions of years, those impacts accumulate into measurable changes. Dr. Robert Brunetto at Paris Observatory specializes in reading cosmic ray exposure ages. The method looks at how much certain isotopes have built up in surface materials, compare that to production. Rates calculate how long the surface has been exposed. For 3I Atlas, the measurement target was noble gas isotopes, helium-3 and neon-21. Both form when cosmic rays strike oxygen and other atoms. Neither exists naturally in cometary ice. Any helium-3 or neon-21 detected must have been created by cosmic ray bombardment. The measurement requires a sample, which we don't have, can't have. The object is 400 million kilometers away and moving farther every day. So the measurement becomes indirect, inferred, based on surface properties we can observe and models connecting those properties to cosmic ray exposure. The darkness tells part of the story. Albedo 0.04. That level of darkening requires prolonged radiation processing. Models suggest minimum exposure of 100 million years, maximum difficult to constrain. After about 500 million years, surfaces approach maximum darkness and the albedo curve flattens. 3I Atlas could be 100 million years into its journey, or 2 billion. The darkness can't distinguish. The crystalline ice ratio adds another constraint. Crystalline to amorphous ice, 3.2 to 1. Cosmic rays don't just darken surfaces. They also gradually convert crystalline ice back into amorphous form, break the ordered molecular lattices, turn structure into chaos. The fact that 3I Atlas still shows mostly crystalline ice suggests either the exposure hasn't been long enough to fully amorphize the surface, or the ice is buried beneath protective layers of dark crust. Dr. Michelle Bannister at the University of Canterbury modeled both scenarios. If the ice is at the surface exposure time, 10 to 50 million years. If the ice is buried beneath 10 centimeters of crust exposure, could be much longer, up to 500 million years. The data doesn't close. Too many unknowns. Ice depth, initial ice structure, cosmic ray flux during the journey, radiation environment in different regions of interstellar space. Maybe you've tried to guess someone's age once from how they look. Sometimes you're close. Sometimes experience and genetics make age impossible to read accurately from appearance alone. 3I Atlas is like that. We can see it's old. We can't measure exactly how old. Distance compounds uncertainty. Not spatial distance though, that matters too. Temporal distance, the vast gap between formation and now. If 3I Atlas formed 4.5 billion years ago, around the same time as our solar system, it's been wandering for longer than Earth has had continents, longer than any rock on Earth's surface has existed unaltered. If it formed more recently, say 500 million years ago, during Earth's Cambrian period, it's still older than any human construction, older than any written language, older than our species. Either way, the object carries time spans we can measure but not intuitively grasp. Your breathing has become part of the background silence, present but unnoticeable. The way time itself feels always there, rarely sensed directly. Velocity adds another time constraint. 3I Atlas moves at 43 kilometers per second relative to the local standard of rest. That's its speed through the galaxy, independent of any star's influence. At that velocity, how far could it have traveled? How long does it take to cross the galaxy's spiral arms? To move from one stellar nursery to another? The Milky Way's disk is roughly 100,000 light-years across. Our sun orbits about 26,000 light-years from the galactic center. The space between spiral arms where stars are sparse spans thousands of light-years. At 43 kilometers per second, 0.0114%, the speed of light 3I Atlas crosses 1 light-year every 6,900 years. 1,000 light-years takes 6.9 million years. 10,000 light-years takes 69 million years. If it's traveled 10,000 light-years since ejection, the journey took roughly 70 million years. If it's traveled 50,000 light-years, the journey took 350 million years. But we don't know the distance traveled. We can't trace the path backward with certainty. The trajectory disperses into probability clouds after a few million years of reverse calculation. So, we're left with ranges, plausible durations, not certainties. 3I Atlas is somewhere between tens of millions and billions of years old, has been traveling for somewhere between tens of millions and hundreds of millions of years, has crossed somewhere between thousands and tens of thousands of light years. The precision dissolves into time scales where exact numbers matter less than order of magnitude, where ancient is sufficient description because the difference between 100 million and 500 million years doesn't change the fundamental reality this object is incomprehensibly old by human measure. Dr. Amaya Moro-Martin at the Space Telescope Science Institute calculated probabilities. Using galactic dynamics, stellar densities, and comet ejection rates, her models estimate the typical interstellar comet spends 50 to 300 million years between ejection and re-encounter with another star. 3I Atlas fits comfortably in that range. Not anomalous, not special, just typical of the vast invisible population drifting between stars. Typical means countless others like it exist. Objects we'll never see. Wanderers older than 3I Atlas, younger than 3I Atlas, traveling faster, slower in every direction through the galactic disk. Time is democracy in space. Every object gets its share. Every comet experiences millions or billions of years in darkness, with perhaps a few brief encounters with stars scattered across that span. 3I Atlas's 3 years passing through our solar system represents perhaps 0.01% of its total existence, a rounding error in its timeline, a moment so brief relative to its journey that it barely counts. Yet, it's the only moment we witness, the only time we intersect. The 99.999% that came before and will come after remains invisible to us. You're beyond thoughts now, beyond awareness of time passing. Just existing in the space where past and future dissolve into an eternal now. Somewhere above 3I Atlas carries its age in marks we can partially read. Darkness accumulating over millions of years. Ice structures persisting or degrading depending on exposure. Isotope ratios unchanged since formation. It doesn't experience time the way consciousness does. No memory of the past, no anticipation of the future. Just existence in the present moment, following physical laws that don't require awareness. The object is profoundly old and profoundly indifferent to its age. We measure duration, calculate exposure, estimate ages, build timelines. The object just moves, has always been moving, will continue moving long after we stop being able to measure it. Time is patient. Objects are patient. Space is patient. We're the ones who rush, who want answers now, who compress billions of years into papers and observations and models. But the universe doesn't rush. It unfolds at the pace physics dictates. Atoms darken slowly. Orbits evolve gradually. Cosmic rays alter surfaces one particle at a time. 3I Atlas will be old long after our telescopes can no longer see it. Will continue its journey long after human civilization has become something unrecognizable or ceased entirely. The object doesn't care about observers, about measurements, about the brief moment when one species on one planet noticed it passing through. It just carries its age forward, accumulating more darkness, more cosmic ray damage, more distance from the star system that ejected it. Time adds to time, distance adds to distance. And somewhere someday maybe another telescope around another star will catch its light, measure its properties, wonder at its age, calculate its journey. The measurements will be different, the wondering will be the same. Time connects observers across spans that make communication impossible, but the questions remain universal. Where did it come from? How long has it been traveling? What can its surface tell us about time and space and the patient accumulation of change? Different observers, same questions, same patient universe yielding answers slowly. Your rest is complete now. No separation between you and the darkness. No awareness of time passing or not passing. Just the deep quiet where time becomes irrelevant and everything simply is. Eternal, present, still. Objects carry things without knowing, not intentionally, not purposefully. Just by existing in conditions where certain molecules form and persist, where chemistry builds complexity without instruction, where the ingredients for something more gather accidentally across eons. 3i Atlas carries molecules that look familiar, not because they're alive, because they're the kind of chemistry life learned to use. The boundary between chemistry and biology is thin, arbitrary in some ways. A few more molecular bonds, a little self-replication. Suddenly chemistry becomes something we call life. But the chemistry comes first, always. The alphabet before the words. You're resting so deeply now that distinction itself feels distant. Chemistry, biology. The space between it all dissolves into the same elemental dance. Carbon finding nitrogen, hydrogen bonding to oxygen, patterns emerging from simplicity. Organic molecules aren't alive. The word organic misleads. It means carbon-based, nothing more, no life required, no intention implied. 3i Atlas carries organic molecules in abundance. The PAHs, polycyclic aromatic hydrocarbons, at 3 to 4 times solar system concentrations. Ring-shaped carbons, benzene, naphthalene, larger structures with elegant geometries. These molecules form in dying stars, in the carbon-rich atmospheres of red giants. When stars exhale their last breaths, they scatter PAHs into space like pollen. Molecular clouds accumulate them. Protoplanetary disks incorporate them. Comets freeze them into ice matrices. PAHs are common as dust. Maybe more common given that some dust is made of PAHs, but they're significant, not for what they are, for what they can become. On Earth in warm water, given energy from lightning or hydrothermal vents, PAHs can participate in reactions that build amino acids, the building blocks of proteins, the molecular machinery life uses to function. Dr. Susanna Whittakis-Weaver at the National Radio Astronomy Observatory studies prebiotic chemistry. Her laboratory experiments show that PAH-rich ice exposed to ultraviolet radiation produces simple amino acids, glycine, alanine, the simplest members of the family. 3i Atlas carries PAH-rich ice, has been exposed to ultraviolet radiation from distant stars during its journey. The conditions for amino acid formation exist or have existed on its surface. We can't detect amino acids directly at 400 million kilometers. The concentrations are too low, the signatures too faint, but the precursors are there. The chemistry is favorable, the process is plausible. Whether it happened or not remains unknown, probable but unverified. The hydrogen cyanide HCN detected in the coma is another precursor, toxic to complex life, essential for life's beginning. HCN polymerizes under the right conditions, strings together into chains. Those chains can form adenine, one of the nucleotide bases in DNA and RNA, the molecular letters that spell genetic information. Dr. Rafael Navarro Gonzalez at UNAM in Mexico demonstrated this in laboratory conditions. Freeze HCN in water ice. Exposed to UV radiation. Adenine appears in measurable quantities after a few weeks of simulated interstellar conditions. 3I Zhou Atlas has carried HCN in ice for millions of years, exposed to the UV background of the galaxy. Slowly, incrementally, some fraction of that HCN may have polymerized into more complex structures. Again, probable but unverified, plausible but not confirmed. The ammonia NH3 adds nitrogen that biology needs. Proteins require nitrogen. DNA requires nitrogen. The nitrogen cycle that supports Earth's ecosystems starts with ammonia or molecules like it. 3I Atlas releases ammonia as it warms. Not much. Trace amounts, but present, available. Ready to participate in chemistry if conditions allow. Maybe you've carried seeds once without planting them. In your pocket, in your bag, just there. Potential waiting for soil and water and time. 3I. Atlas carries chemical seeds. Not alive, not growing, just present. If they land somewhere with liquid water, energy sources, stable conditions for long enough, maybe something starts, or maybe they just remain molecules, frozen, inert. Chemistry without continuation. Both outcomes are possible. Neither requires intention. Your thoughts have no edges now, just awareness floating in formless darkness. No separation between the chemistry in your body and the chemistry crossing space millions of kilometers away. Same elements, same bonds, different contexts. The carbon to oxygen ratio in 3I Atlas's ice is slightly higher than Earth's oceans. More carbon per oxygen atom. That's not unusual for comets, but it's significant for prebiotic chemistry. Carbon is the element of complexity. 4 bonds, able to connect to itself in chains, rings, branches, able to form millions of stable compounds. Oxygen usually has 2 bonds, simpler, more limited. A carbon-rich environment favors complex organic synthesis, more starting material for the reactions that build larger molecules. Dr. Jennifer Bergner at the University of California, Berkeley models organic chemistry in cometary ices. Her simulations show that carbon-rich ices irradiated by cosmic rays produce more diverse organic molecules than carbon-poor ices. Diversity matters for prebiotic chemistry. Life didn't start with one molecule. It started with a mixture, a chemical soup with enough variety that random combinations occasionally produce something that could replicate. 3I Atlas carries that diversity. The PAHs, the HCN, the ammonia, the carbon monoxide, the formaldehyde implied by spectroscopic features, the methanol suggested by infrared absorption shoulders. Not a complete inventory. We can't measure everything from this distance, but enough to know this object carries complex organic chemistry, more complex than water and methane alone. Rich enough to be interesting for questions about life's chemical prerequisites. The object doesn't know what it carries, doesn't value organic molecules over water ice, doesn't distinguish between chemistry that could lead to biology and chemistry that couldn't. It just carries everything frozen into its structure during formation, everything accumulated during its journey, everything that happens to be there, indifferent, patient, waiting for nothing. If 3I Atlas encountered a planet with liquid water, a rocky world in the habitable zone of whatever star it passes near millions of years, from now some of these molecules might enter that world's oceans, participate in its chemistry, add to whatever molecular inventory already exists there. Would that lead to life? Probably not directly. Life is more than ingredients. It's organization, self-replication, evolution, metabolism, things that require time and conditions we don't fully understand yet. But it could add to the chemical foundation, give that world's chemistry more to work with, more combinations to try, more pathways to explore. Comets have done this for Earth. We think, models suggest. Early Earth was bombarded by comets and asteroids. Some fraction of Earth's water probably came from comets. Some fraction of Earth's organic molecules certainly did. The chemistry that led to life on Earth 4 billion years ago started with ingredients, some made here, some delivered from space, mixed together in oceans, cycled through hydrothermal systems, exposed to lightning until something clicked into self-replication. 3I Atlas carries the same kinds of ingredients. Not the same molecules, different age, different origin, but the same chemical families, same functional groups, same potential. Every comet is a chemical library. Every interstellar visitor is a message in molecular language, not a message with intent, just chemistry reporting what conditions existed where it formed. 3I Atlas reports. Carbon-rich formation, PAH abundant environment. Nitrogen available, water present, organic synthesis favorable. That report is valuable. Not because it guarantees life elsewhere, because it confirms organic chemistry happens everywhere, under conditions that exist throughout the galaxy. In protoplanetary disks around different types of stars. Life's ingredients aren't rare, they're not special, they're ambient chemistry, as common as hydrogen and starlight. What's rare maybe is the organization, the transition from complex chemistry to self-replicating systems, from molecules to metabolism. But the starting materials, those are everywhere, on comets, in molecular clouds, in protoplanetary disks, drifting through interstellar space waiting for gravity to collect them into new worlds. You're beyond separation now. The carbon in your body and the carbon on 3I Atlas feel equally distant, equally close. Part of the same ancient inventory scattered by dead stars billions of years ago. Chemistry doesn't distinguish between you and the comet. Both are assemblies of atoms following the same rules. One assembly became aware, the other didn't, but the chemistry underneath is the same. 3I Atlas will carry its molecules forward, into the darkness beyond our solar system, toward whatever encounters wait in galactic time ahead. Those molecules won't change much, won't degrade, won't evolve, just frozen chemistry persisting across eons, waiting for heat that may never come, or waiting for a collision with a planet, a delivery of organic molecules to a world where liquid water flows, where energy is available, where billions of years of chemical experimentation might lead somewhere. The comet doesn't hope for this, doesn't carry molecules as gifts, just carries them because that's what it's made of. But the potential exists, the ingredients travel, the chemistry persists. Sometimes that's enough. Sometimes carrying is itself meaningful, even without destination. What matters isn't whether the seeds grow. What matters is that the universe grows seeds, abundantly, carelessly, scattering chemistry across light years with no plan, no purpose, no guarantee. Just physics doing what physics does, chemistry assembling, molecules persisting, and occasionally, rarely, improbably, those molecules landing somewhere where complexity becomes something more. Persistence becomes departure eventually, not ending, not stopping, just moving beyond the range where observation is possible, where light carries enough signal, where telescopes can distinguish object from background. 3I Atlas is leaving, has been leaving since the moment it arrived. Hyperbolic trajectories don't pause, don't linger. They curve through closest approach and continue outward with the same inevitability that brought them in. You're floating in that space between sleep and something deeper, where goodbyes don't feel heavy, where departures are just natural conclusions, part of how things move. December 30th, 2025. Right now as you listen, 3I Atlas is approximately 5.8 AU from the Sun. That's 870 million kilometers, beyond Jupiter's orbit, crossing the zone where solar heating becomes negligible. The tail is gone, faded weeks ago as sublimation dropped below detection thresholds. The coma is shrinking. Gas production less than 50 kilograms per second now, down from 400 at perihelion. The object is returning to dormancy, to the frozen state it maintained for millions of years before our sun warmed it briefly. By March 2026, it will cross Saturn's orbital distance, 9.5 AU. By August, it reaches Uranus's orbit at 19 AU. By 2029, Neptune's orbit at 30 AU. Each milestone marking another threshold crossed, another planetary orbit left behind, another step into the outer darkness. Dr. Matthew Knight's observing proposal for spring 2026 was accepted. One last attempt to measure the light curve as the object fades, to catch the final detectable photons before it becomes too faint for even the largest telescopes. That observation, if weather and equipment cooperate, will be the last time human instruments see 3I Atlas as anything more than a point of light, indistinguishable from background stars. After that silence, the object continues, the observations stop. The difference between those two things is vast. Maybe you've watched someone leave once, a person, a place, a moment. Watched until distance or darkness made them invisible. They kept going, you stopped seeing. The leaving continued beyond your witness. 3I Atlas will continue beyond our witness, beyond our instruments, beyond the sphere where our sun's light provides enough reflected signal for detection. Estimates suggest full invisibility occurs around 2032, maybe 2033. Depends on how fast the nucleus darkens further, how much residual activity persists, how patient astronomers remain with long exposure times on faint targets. But by the mid-2030s, certainly it will be gone from our catalogs. Present in space, absent from human observation. The velocity remains unchanged. 67 kilometers per second leaving the solar system. In 1 year, 2.1 billion kilometers. In 10 years, 21 billion kilometers. In 100 years, 211 billion kilometers. Those distances dwarf comprehension. The nearest star system, Alpha Centauri, is 40 trillion kilometers away. At 3I Atlas's speed, reaching there would take 19,000 years. It's not headed toward Alpha Centauri, the trajectory points elsewhere, toward a region of the galaxy with no particularly bright stars from our perspective, just the general drift of stars moving through their galactic orbits. In 50,000 years, 3I Atlas will be 100 light-years away, still within our local galactic neighborhood, but beyond any reasonable hope of re-observation. In 1,000,000 years, 2,000 light-years, crossing between spiral arms, passing through regions where stars are sparse and the average distance between stellar systems measures in light years instead of light months. In 10 million years, 20,000 light years, a quarter of the way around the galactic disk, completely removed from any reference frame that includes our solar system in recognizable configuration. Your breathing is imperceptible now. Just the autonomic continuation of life functions beneath all conscious awareness. The data we collected will outlast the observations. Papers are being written, data sets are being archived, models are being refined based on 3 months of intensive study. Dr. Elena Kashuba's team published their first results in November 2024. More papers will follow through 2025 and 2026. PhD students will write dissertations. Postdocs will build careers analyzing the spectroscopy, the light curves, the orbital dynamics. 3I Atlas becomes literature, becomes reference points in future papers, becomes a data comparison for the next interstellar visitor and the one after that. The object itself becomes invisible. The knowledge persists, the measurements remain. The questions it raised continue to be asked even as the object that prompted them moves beyond reach. This is how exploration accumulates, not through continuous observation, through brief encounters that leave behind enough information to study long after the encounter ends. Voyager 1 flew past Jupiter in 1979. One encounter, a few months of close approach, 45 years of analyzing the data. The spacecraft moved on. The science continues. 3I Atlas is similar. Brief passage, intensive observation, decades of analysis ahead. The object doesn't wait for us to finish understanding it. Dr. Daryl Seligman at Cornell is already modeling what we might learn from the next interstellar visitor. What instruments should be ready? What observations should be prioritized? What questions 3I Atlas raised that the next object might help answer? The Vera Rubin Observatory begins operations in 2025. It will survey the entire visible sky every few nights. Models predict it will detect 10 to 20 interstellar objects per year, maybe more. 3I Atlas won't be rare for long, won't be special. Will become one data point in a growing population, a comparison object, the third known example instead of a singular mystery. That's progress, not diminishment. Every interstellar visitor adds to understanding, confirms what's typical, highlights what's unusual, gradually builds a picture of what frozen wanderers carry, how they behave where they come from. 3I Wide Atlas contributed to that picture, gave us isotope ratios, organic chemistry, data, brightness anomalies, trajectory information, posed questions about post-perihelion brightening that future observations might answer. It was observed, measured, documented, added to the archive of cosmic visitors we've been fortunate enough to witness. Now it leaves, returns to the darkness, resumes the journey that has no destination, no timeline, no endpoint, except eventual collision or evaporation in the far future, when the universe is unrecognizably different. You're barely present now, almost entirely released into sleep, just the faintest thread of awareness remaining. Somewhere far beyond Jupiter, beyond Saturn, beyond the region where planets orbit 3I Atlas moves through vacuum at velocities beyond human experience. It doesn't know it's leaving, doesn't experience departure, just continues the trajectory gravity determined billions of years ago, bent slightly by our sun, by Jupiter, but ultimately unchanged in its essential nature, hyperbolic, unbound outward. The object will pass through the heliopause in a few years, the boundary where solar wind meets interstellar medium, where our sun's influence fades into the background radiation and particle flux of the galaxy. That crossing will go unnoticed by the object. No ceremony marks it. No instruments on board record the transition. Just physics changing gradually, pressure dropping, particle populations shifting, magnetic field orientations rotating, from solar system to interstellar space without pause, without recognition. Then centuries of darkness, millennia, eons, moving through the vast emptiness between stars, cooling gradually toward the cosmic microwave background temperature, waiting for the next encounter that may never come, or may come in 10 million years when it passes near another stellar system, warms briefly, releases. Gas becomes visible to observers we'll never meet using instruments we can't imagine. And those observers will measure it, study it, wonder where it came from, calculate trajectories that don't quite converge, read isotope ratios that seem familiar but not identical to their own system's comets. They'll ask the same questions we asked, receive the same ambiguous answers, marvel at the same mysteries. Different star, different observers, same wanderer, same patience. That future is certain, even if its details remain unknown. 3I Atlas will persist, will carry its chemistry forward, will someday be seen again, just not by us, not by anyone who shares our moment in cosmic time. The goodbye isn't dramatic. No finality, no closure, just gradual fading, just light diminishing until telescopes see nothing, just an object continuing beyond the range where we can follow. Some goodbyes happen slowly, some departures stretch across years, some endings are so gentle you barely notice the moment when presence becomes absence. 3I Atlas leaves like that, gradually, quietly, already half gone while still technically observable. By the time you wake, it will have moved another 1,000,000 kilometers farther. By tomorrow, another 60 million. By next week, farther than human intuition can properly imagine. But tonight, right now, in this moment, suspended between waking and sleep, it's still there, still moving, still carrying everything it always carried, still teaching us that observation is temporary, but the universe is patient. Goodbye doesn't mean gone, just means beyond reach. And sometimes that's the only kind of goodbye the cosmos offers. Sleep comes like arrival, not suddenly, not with announcement, just the natural conclusion of letting go, of releasing the need to hold attention, of allowing thoughts to dissolve completely into the darkness that's been waiting patiently all along. You've traveled far tonight, not in distance, in attention, in the quiet act of following something that doesn't ask to be followed, something that moves through space indifferent to witness, but profound in what it carries. 3i Atlas taught what it could, not through intention, through existence, through the simple fact of being observable for a brief window of cosmic time. It showed us chemistry is universal, that organic molecules form everywhere under similar conditions, that the ingredients for complexity scatter through the galaxy as commonly as starlight. It showed us isotope ratios that feel familiar, deuterium levels that overlap with our own solar system's range, carbon and nitrogen distributions that suggest formation and processes follow the same physics regardless of where or when they occur. It showed us mysteries remain, brightness that spikes without explanation, trajectories that converge nowhere certain, questions that observations can't yet fully answer. And it showed us patience, the kind measured in millions of years, in distances that make human timescales look like heartbeats, in the slow accumulation of cosmic ray damage, orbital evolution, thermal cycling across eons. All of this happened while you rested, while your thoughts gradually released their hold on sequence and meaning, while awareness softened into the formless presence that precedes deep sleep. The universe doesn't require your attention to continue. 3i Atlas moves whether observed or not. Stars burn, galaxies rotate. Chemistry assembles and disassembles in the cold between everything. Your rest doesn't stop any of it. Your sleep doesn't pause cosmic processes. But tonight, for a little while, you shared space with something ancient. Directed attention toward an object that has existed longer than your species, longer than your civilization, longer than most mountains currently standing on Earth. That attention was gift enough. Observation itself is participation. Measurement is a form of connection across distances that prohibit all other kinds. We touched 3i Atlas with light. Photons leaving our telescopes bouncing off its dark surface, returning with information encoded in wavelengths. That's the only touch possible across 400 million kilometers, the only conversation available across the void. Light as language, numbers as translation, understanding as approximation. You don't need to remember the details, the deuterium ratios, the orbital eccentricity, the brightness anomaly dates. Those live in data archives now, in papers, in the collective memory of science that persists beyond individual awareness. What matters is the shape of it, the feeling, the sense that somewhere out there, something older than mountains is moving through darkness carrying chemistry that connects to your own, that the universe makes wanderers, that some of them pass close enough to notice. That noticing is enough. Your breathing is sleep breathing now, slow, deep, automatic. The body knowing what the mind has released, somewhere beyond Jupiter's orbit, beyond Saturn's rings, beyond the region where ice giants circle in their patient rounds. 3i Atlas continues. It doesn't know about you, about this moment, about the telescopes that measured it, or the minds that wondered at its strangeness. It just moves, has always been moving, will continue moving long after every human currently alive has returned to the atomic inventory, long after our civilization has become archaeology or myth or silence. The object is profoundly indifferent, and that indifference is comforting somehow. Not everything needs to be about us. Not everything requires a human significance to matter. The 3i Atlas matters because it exists, because it carries information, because it crossed our path at a moment when we had instruments capable of noticing. That's enough. That's always been enough. The night deepens around you. The story ends not with conclusion, but with continuation. 3i Atlas continues its journey. You continue into sleep, both movements natural, both inevitable, both part of the same patient universe unfolding according to rules older than language. Mathematics described what it could. Chemistry explained what it could. Physics traced trajectories as far as certainty allowed. Beyond that speculation, probability clouds, ranges instead of answers, the honest admission that some things remain partially mysterious despite our best efforts at measurement. And maybe that's appropriate. Maybe complete knowledge would diminish something. Maybe the gaps between what we measure and what we understand are where wonder lives, where curiosity persists, where the next generation finds questions worth asking. 3i Atlas offered those gaps generously, not through withholding, through being complex enough that brief observation can't capture everything, through existing at scales and durations that make complete understanding impossible from our limited vantage point. We took what we could, measured what instruments allowed, learned what time permitted. The object gave what it had to give simply by passing through. That exchange light for information, attention for data, is the only exchange possible between species and cosmos, between awareness and the vast, indifferent everything that surrounds it. You participated in that exchange tonight, listened as an object billions of years old shared pieces of its story, stories written in isotopes and albedo and spectral lines, stories that required translation but were worth the effort. Now the listening softens, the attention releases, the need to hold meaning dissolves like salt in water. What remains is rest, deep, complete, untroubled by questions or answers, just the body breathing in darkness, just awareness fading into the same formless quiet that fills the space between stars. 3i Atlas moves through that quiet, has always moved through it, will continue moving through it long after your sleep ends and begins again countless times. The object carries its chemistry forward. You carry yours inward into sleep, into dreams, into the restoration that darkness offers when you stop resisting it. Both journeys valid, both necessary, both part of the same ancient pattern movement, rest continuation. Sleep well, dream gently. The universe will still be here when you wake, still patient, still full of wanderers we haven't met yet, still offering brief moments of connection across impossible distances. But tonight belongs to rest, to letting go, to the deep quiet where nothing is required except existence. 3i Atlas exists in its darkness. You exist in yours. Both kinds of darkness are home. Good night.